the fastest passenger train on the planet.
It's flying pretty much at 431 kilometers an hour.
Seemingly defying the very laws of nature.
The train floats at 1 centimeter from the guideway.
And the pioneering historic innovations.
Wow, it looks like something out of the future.
I don't think without the owl we would have had this great, vibrant American city that we have today.
That made the impossible possible. China is a country on the rise, and it's aiming for the stratosphere. Shanghai is a global and financial hub, which attracts people from all over the world with its ambition. As the influx of people increases, so too does demand for space. The city faces heavy traffic jams and congestion on a daily basis.
Shanghai is busy. Cars as well as buildings fight for space on the ground. It can be very difficult to move around.
By the beginning of the 21st century, Shanghai faced a seemingly impossible engineering challenge. An increasingly congested 8-lane highway was Shanghai's only link to the important Pudong International Airport. And traffic was getting worse.
To get to the airport by car, it takes 45 minutes to travel just 40 kilometers. You really need something to cut through the city to get to the airport without stopping and without encountering any other vehicles. I, like most people in this city, don't have time to sit in traffic.
The solution would be the Shanghai Maglev, or Transrapid. A futuristic concept currently unique in the world.
The thing that's different and very unique about the Maglev is the fact that it floats. It hasn't got any wheels, it floats across the guideway all the way to the airport. Now the Maglev is just about to pull out of the station. When it's at its top speed, it'd be moving at 431 kilometers an hour. That is just beyond belief. Incredible.
In order to create this modern marvel, the designers and engineers of the Maglev would have to overcome several apparently impossible challenges. The Maglev's creators were planning to throw away several of the key historic engineering innovations that are the mainstay of current train travel. First, the train would be engineless. And it would do away with one of engineering's most fundamental inventions. Not only that, it would seemingly challenge the most basic of principles. But for the designers of the Shanghai Maglev, the problems begin before they can even conceive the train. How to fit a brand new transport system into an already busy and growing city.
Shanghai is one of the most heavily populated cities in the world, and the population is increasing. Now, building the infrastructure it needs is very challenging just because there is no space. Like all the buildings around here, the only place really to build is to go up.
Chicago is one of the world's busiest modern metropolises. The logistical challenge of moving its inhabitants is huge. Yet, thanks to the work of some of the city's pioneering engineers, the solution they implemented well over 100 years ago is still in use today.
In the late 19th century, Chicago is one of the fastest growing cities, if not the fastest growing city in the world. In the 1840s, shortly after the city was established, we had roughly about 4,000 people. And by 1900, we've got over 1.5 million. Our city is rapidly expanding. It's almost the Shanghai of the late 19th century.
So how could engineers and planners deal with the seemingly impossible challenge of transporting a growing population without clogging the already busy city streets further?
So this is the solution that was developed to elevate the city's rail lines above the street traffic. Although it's not cheap to do this type of infrastructure, it is cheaper, of course, than building subways.
Work began in 1892. But building a railway 30 feet above established city streets required a massive engineering effort and was at first not welcomed by everybody. Third-floor apartment dwellers now had to keep their curtains drawn if they wanted privacy. And young women were warned to be careful of roving rail-borne peeping toms. Nevertheless, for the masses, the system was a big hit. It was lovingly nicknamed the L, short for elevated.
We're here at Quincy. This L station has been restored, and it gives us a sense of what commuters would have seen in the late 1890s. And the basic concept of moving people in and out of the city at a different level than street level has not changed since then.
Elevating the city's railways was a solution so successful that more than 120 years later, it's still transporting around 500,000 passengers every single weekday.
The growth of the L and the growth of Chicago are synonymous. The boom of population in the late 18th century follows right along with the growth of this transit system. And I don't think without the L we would have had this great, vibrant American city that we have today.
Engineers in Shanghai have taken the Chicago solution of an elevated railway and created a 30-kilometer-long guideway soaring above Shanghai's streets.
The advantage a system like this has in already built-up urban spaces is it's very easy to install. It doesn't interfere with underground services. It doesn't interfere with existing infrastructure at ground level, which is really good.
But building an elevated railway in Shanghai means overcoming a very specific, potentially catastrophic danger.
Shanghai sits in an area of great seismic activity. It also has weak clay soil. The risk of liquefaction is very high.
Liquefaction is an unusual and dramatic effect that can occur during earthquakes, when seemingly solid ground mysteriously turns to mush. Physicist Andrew Steele has prepared a simple demonstration to show just how liquefaction works.
So this water represents the groundwater. This ground has got a very high water table, so it's only got a thin layer of dry soil on top of the saturated soil underneath. So imagine you build on this land. You construct your beautiful city. But you built on sandy soil and you built on a fault line, so there's the danger of an earthquake. You can see that as you shake it, then the groundwater is forced up into the top layer of the soil, and that changes its state from that of a solid to very much behaving like a liquid. And the buildings are just sinking straight into it.
With earthquakes a constant threat in Shanghai, measures would need to be taken to make sure the Maglev didn't sink into the soft ground the next time one hit.
Engineers came up with a technique called piling. Each support pier was built on top of concrete cap, about 2 meters deep and approximately 12 meters wide. Underneath the cap are 20 to 24 concrete piles that were driven to depths of a staggering 70 meters.
The concrete caps provide a solid base, which is supported by the multiple piles. So, if the soil near the surface liquefies, the deep roots will hold the Maglev guideway firm. In double-quick time, Chinese engineers constructed over 2,500 concrete columns to support the guideway.
It took less than 9 months to sink foundation piers every 25 meters along the entire 30-kilometer route.
However, engineers had further challenges to face, and they'd have to turn to the great innovators of the past.
Ooh, that was fast.
To produce more impossible engineering. The Shanghai Maglev is the fastest passenger train on the planet. A vision of the future that literally flies along the ground at a staggering top operating speed of 431 kilometers per hour. This piece of impossible engineering has transformed travel between Shanghai's airport and the busy cutting-edge metropolis.
The Maglev runs all the way from here to Pudong Airport, which is a 34-kilometer journey in that direction. Now, if I was to get the metro, it would take me over an hour. If I got a cab, it would take me 40 minutes or so. But if I got the Maglev, which I like to do, it takes me only 7 minutes.
Creating a train this fast presented engineers with major challenges.
This would be the fastest train in the world. But trying to get a train up to speeds pushing 500 kilometers an hour, designers would be faced with the problem of wind resistance or drag. The greater the speed, the greater the resistance, and all this air movement has the potential effect of slowing the train down and wasting valuable energy.
The earliest evidence of primitive railways can be traced back to ancient Greece, where men and animals pulled wheeled vehicles that ran in limestone grooves, thus preventing the wagons from leaving their intended route. Railed transport was devised as a way of reducing friction. In England in 1805, it was demonstrated that a good horse on an ordinary road could pull a wagon weighing a ton. But on rails, it could pull a train of 12 wagons, each weighing 3 tons with ease for 6 miles in 2 hours. Add steam power, and whole continents could be crossed with ease, transforming the modern world. Despite the railways dramatically changing the way we live, by the 1930s, aerodynamic design had stood surprisingly still.
Train design fundamentally hadn't changed for 100 years since this, Stephenson's rocket. You can see the classic cylindrical boiler, we've got the smokestack at the front, and this completely snub, flat, unaerodynamic nose.
It would take a radical thinker to come up with a plan that would change train design forever. In the north of England, steam locomotive engineer Nigel Gresley produced a new, sleek machine that would be the fastest train in the world. The Mallard.
Everything about this locomotive is designed to go as fast as possible. You've got these massive wheels driving it forward. We've got a double chimney to suck out the exhaust as quickly as possible at high speed. And then you've got this beautiful streamlined shape, in stark contrast to the trains that had come before.
In order to create his design, Gresley used a wind tunnel, previously the preserve of aviation, and found some interesting results. Andrew Steele is visiting test centre The Train Rig in Derby to see what a difference a streamlined design can create.
This is the test track. It's 150 metres long, and we can accelerate trains to 75 metres a second, which is over 250 kilometres an hour. Today, we've got two different trains that we're going to be testing. This is a flat-nosed freight train, which represents sort of an unaerodynamic train as they were originally designed. And this one here is a high-speed train, got this sloped nose. We're going to see what difference that makes to the speed the train can travel at. And this is what we're going to be using for the actual experiment. These things here are light gates, and when the train goes past this one, it interrupts the light beam, and we can detect that time. Then a fraction of a second later, it'll go past this light gate, interrupts this beam, and by measuring the difference between those two times, you know this distance here, so we can work out exactly how fast it's going.
The model trains are fired using giant rubber catapults.
So we're just applying some tension to the track now, and that's pulling the train back into the firing position. I'm almost as tense as the train is. Okay, so just, here he goes. Ooh. That was fast. Ooh. And believe it or not, that was a sort of slow test run. So now we've done that test run, the key thing is to find out the readings that we got from these light meters. We've got two readings here. At the first set of light gates, it was doing about 36 meters per second, but then by the time the second set of light gates, just a couple of meters later, it's only doing 34.5 meters a second. So you can see it's lost some speed, the aerodynamic drag has kicked in and slowed the train down.
In the short distance between gates, the flat-nosed train loses around 5% of its speed. Next to be tested is the sloping-nosed model.
Ready, aim, and fire. Wow.
This time, the model speed reduces by only 2% between the light gates.
So these numbers, they're quite subtly different, but when you scale it up to a full-size train and you're looking to propel it constantly down the track, this can translate into a big change of efficiency.
A fact Nigel Gresley spotted and exploited brilliantly.
Gresley's engineering really was a complete step change. Although we'd used aerodynamics in planes and hydrodynamics was known about in boats, this was the first time those principles had been applied to a train. And that's what enabled a Mallard to travel at 126 miles per hour.
In 1938, the Mallard set the record for the fastest steam train on rails, a record which still stands today. Designers of the Shanghai Maglev have learned from the breakthroughs made by the Mallard and created a train that travels at speeds that innovator Nigel Gresley would have thought impossible. In one test run, it exceeded 500 kilometers per hour. Way over twice what the aerodynamic Mallard was capable of.
You can see it has a very sleek, streamlined design with the very smooth, sloping nose. Also, the train wraps itself around the guideway, which reduces turbulence that might otherwise be generated between the train and the track.
But the development of the futuristic Maglev system took decades of experimentation before it reached its incredible 21st century performance levels. Created in Germany, the first passenger-carrying prototype, the Transrapid Maglev system, was unveiled in 1971. At that time, travelling at speeds where little consideration to aerodynamics was necessary. However, as experiments continued and velocities rapidly increased, the carriage design that now graces Shanghai's elevated track quickly took shape. But with increased speed comes additional engineering challenges.
The maglev going to the airport and the maglev coming from the airport pass each other at incredible speeds, potentially a combined speed of over 860 kilometers per hour. And this could cause a potential problem. However sleek the design, any object passing another at speed creates a change in pressure between them. Lower pressure as the trains are together, followed by a return to a higher pressure once they've passed. This could potentially cause stresses to the cabin walls. So maglevs have been engineered with an aluminium composite shell, light but at the same time strong and stiff enough to support the pressure acting on the structure by high-speed traveling.
To take the Transrapid system to record-breaking speeds, engineers could draw inspiration from a trailblazer of the past.
They combined the principle of the hovercraft and a jet engine, and they smashed the rail speed record.
To create their own impossible engineering. The Shanghai Maglev, the world's fastest passenger train. A unique engineering feat situated in one of China's most ambitious cities.
This maglev here is the only high-speed maglev in the world, and that kind of chimes in with the ambition of Shanghai. People come here to be able to design daring buildings and daring systems.
And one of the most daring of them all is the Maglev. Travelling at a staggering 431 kilometers per hour and seemingly defying nature. But to create this space-age transit system, its engineers would have to conquer some seemingly impossible challenges.
It's not just the wind that provides friction on the train. One of the biggest losses of energy that occurs in a traditional train is produced by the friction between the wheels and the track. The more friction there is, the more power is lost. In a car like this, for example, 1/3 of the fuel is spent on overcoming friction.
To enable it to reach its record-breaking speeds, the Maglev's designers would have to overcome a challenge that only history's most daring engineers have achieved. In the French countryside, physicist Andrew Steele is looking for the remains of a system that could have been every bit as revolutionary as the Maglev.
So here it is, over 50 years old and covered in moss. This is what its creators thought would be the future of high-speed mass transit. A single concrete rail straddled by a train capable of travelling at 422 kilometres an hour, at a time when the speed record for a conventional train was just half that.
So what kind of vehicle was capable of overcoming the forces of friction to travel so fast? The answer lies in a closely guarded warehouse.
I've come to a top-secret location somewhere outside Paris to get a rare look at what could have been the future of land transportation.
Hello.
Good morning. So, where's it kept?
Hidden amongst an assortment of military vehicles collected by Thierry Farge, are the last surviving examples of an extraordinary experiment.
Wow. So this is the Aerotrain?
Yes.
It looks like something out of the future.
Designed by engineer Jean Bertin in the 1960s, the Aerotrain 1 and 2 are the only surviving prototypes for a system it was hoped would change travel forever.
You can see the Aerotrain doesn't have any wheels. Now, that might seem strange, but although wheels have been the basis for land transport for thousands of years, they come with a big disadvantage. Because the wheels rub against the ground, they create friction, and the Aerotrain tries to get round that. Engineers and scientists have been toying with the idea of frictionless travel for some time. The idea is that if you can remove that frictional resistance to motion, then you can make things travel faster and more efficiently. The simplest way to do that might be to levitate it on a cushion of air, and that's the principle behind how a hovercraft works. We've got our own very simple model of a hovercraft here. It's just a CD with the top of a drinks bottle on it, and then a balloon. Before we inject that cushion of air, the CD only moves a very small distance across the table when I tap it. However, what we can do is attach a balloon to this drinks bottle top and see if that makes any difference to the way that the CD moves. So, there we go. You can see that now, with a tiny tap, the CD moves a long way. And just as long as the balloon's got some pressure to force that air down underneath the CD, then it'll keep on moving around freely. But when the balloon runs out, of course, the cushion of air vanishes and the CD is just as hard to move across the table as it was before. In here, we've got the guts of the Aerotrain. And incredibly, there are just two regular car engines which power massive fans, and that blasts air downwards to lift the train up off the ground, and then inwards to keep it centred on the track. That means that the train isn't in contact with the ground or the track, and so that source of friction is removed, and that means that more of the energy from this engine up here, the propeller, can be used to power the train to move forwards. It's 11 metres long, weighs 2.6 tonnes, and yet the air gushing out of these nozzles was enough to keep it floating 2 or 3 millimetres above the track.
By 1967, the Aerotrain was already proving its potential on the test track as a new form of speedy passenger transport.
It planned to build a track for the Aerotrain between Paris and Orly, 65 miles in 35 minutes. Vive la sport!
But for Aerotrain Mark II, Bertin went all out for speed. The Aerotrain 2 was a futuristic hybrid of jet fighter, racing car, train, and hovercraft. And although it looked like something out of a sci-fi movie, the technology itself was fairly basic.
I think my favourite control is this one that goes marche and arrête, so it's basically stop and go just by flicking a switch.
Nevertheless, it was the combination of engineering ideas that made Jean Bertin's Aerotrain groundbreaking.
Bertin's ideas really were revolutionary. They combined the principle of the hovercraft and a jet engine, and this was the first time it had ever been done. Combined, they smashed the rail speed record.
An aircraft jet engine gives initial thrust up to speeds of around 185 miles per hour. An additional rocket motor boosts the MPH to 235.
Sadly, Jean Bertin's dream of friction-free travel died in the 1970s when the French government abandoned the experiments. However, the Aerotrain now has a familiar-looking cousin, over 6,000 kilometers away in China.
The first time I traveled in the Maglev, we hit 400 and I thought, oh my goodness. And then it continued to travel even faster. I could not believe what I was seeing and experiencing. And it's currently doing a top speed flying pretty much at 431 kilometers an hour, and it still feels very comfortable for the speed at which it's traveling. The Maglev is faster than the Formula One car. It is flying along.
This record-breaking feat is possible because the Transrapid Maglev is not a hovercraft like the French Aerotrain, but is instead flying above the track, levitated by powerful electromagnets. A piece of engineering magic that would have been impossible without one of science's great innovators. Born in 1791, the son of a blacksmith, Michael Faraday received little formal education, but would go on to revolutionize the world. His original laboratory still exists at London's Royal Institution,
If I give it a little push.
where physicist Andrew Steele is exploring how Faraday's discoveries made magnetic levitation possible.
Faraday's discoveries revolutionised our understanding of the interplay between electricity and magnetism. And one of the things that this understanding allows us to make is an electromagnet. So an electromagnet is made of a coil of wire. You then need to get the ends of those pieces of wire and plug them into a power supply. And finally, to magnify the magnetic effect, you often place a core of a material like iron in the middle of the magnet. Let's connect this up. And to prove to you that that's magnetic, you can see that even with this extremely simple setup, we can actually get a piece of metal to stick to it. Another crucial fact about electromagnets, if you want to use them for levitation, is that we can change their strength, and we can do that very easily. Just by changing the electric current passing through this magnet, I can turn the current down and make the attraction much weaker, or I can turn the current up and make that attraction get stronger again.
Not only can electromagnets be adjusted or turned on or off at will, but they can also be significantly stronger than ordinary magnets.
If you want to suspend an entire train, you're going to need a pretty powerful electromagnet. And actually, electromagnets are pretty strong. This little one is enough to suspend my entire body weight. And actually, this thing needs surprisingly little electric current. There's less electricity flowing through this device than there is through your hairdryer or your kettle at home. We've got an electrical current flowing through this electromagnet. If we connect it to the piece of metal on my back, then hopefully there should be enough strength to hold me above the floor. And there you have it.
On the Shanghai Maglev, banks of powerful electromagnets are installed into units that sit on the underside of the carriages. Guidance magnets keep the train centred, and support magnets attract the unit to the underside of the track, and so lift the train above. The entire train therefore effectively flies, suspended 10 millimeters below the track. Not only does this make for extremely fast, friction-free travel, but also reduces wear and tear.
Because there's no contact between the train and the guideway, there is no friction, and this means that the train can have a lifetime of up to 50 years with minimum maintenance required.
But to create a train fit for the future, its designers would still have to look to one of history's greatest innovators.
When I put it on the motor and switch on the magnets, something pretty dramatic occurs.
To create yet more impossible engineering. Travelling at an astonishing 431 kilometers per hour, whilst floating on a magnetic field. The Shanghai Maglev is the only high-speed train of its kind operating commercially in the world. But to create this wonder of modern engineering, its German developers would need to overcome some seemingly impossible engineering challenges. Including creating a propulsion system in tune with its futuristic home.
China, like all modern economies, is worried about its carbon emission quota. As development continues, the demand for oil will also likely increase. But China has a limited domestic oil supply. With its current gas-guzzling congestion problems, greener transport initiatives are drastically needed. Otherwise, the city will choke.
The solution would have been impossible without one of history's great engineering innovators. In the late 1940s, one British engineer's experiments would ultimately earn him the nickname, the father of maglev.
This is a sheet of aluminium. When I put it on the motor and switch on the magnets, something pretty dramatic occurs.
Electrical genius Eric Laithwaite developed the first practical linear electric motor, creating an effect he later dubbed the magnetic river.
First of all, it will levitate or support an aluminium plate. It will guide it sideways, and it will also propel it along.
The linear motor essentially takes a traditional coiled electric motor and unrolls it. Instead of spinning a rotor, what was the coil or stator provides a bed that drives the object along its length.
And there you have your modern vehicle being guided, lifted, and propelled, all by means of the same set of coils.
Laithwaite's experiments provided the key that unlocked the potential of the maglev. The German builders of the Transrapid Maglev system constructed a series of stator blocks that are the main component of the linear motor and act as the propulsion system for the train. Once installed, they were tested in Germany, and in combination with the support and guidance magnets, enabled this unique vehicle to levitate. Relocated to Shanghai, the maglev vehicle travels at well in excess of 400 kilometers an hour without an onboard engine.
A linear motor is embedded into the guideway for its full 30 kilometers. But don't be fooled into thinking this whole track is electrified all the time. What is so brilliant about this system is that only the sections of the track on which the vehicle moves is powered at any time. So as it sets off, the 30 kilometers of track ahead of it is dormant, and only the section in front of the maglev turns on. As soon as the maglev has passed over the short section of track, it turns off again, as the job of pushing the maglev along is taken up by the next section of track, and so on, all the way to its destination.
Having a levitated train travelling at such speed creates several unique engineering challenges.
There's a carriage hurtling along at over 430 kilometers per hour. So it is critical to control fluctuations in the magnetic field and maintain an even gap between the train and the track, no matter how many passengers are on board or what variations there are in the load it's carrying.
With a mere 15 centimetres between carriage and guideway, any errors could see the train crunch into the track. The solution, as physicist Andrew Steele demonstrates, relies on sensors constantly regulating the current in the electromagnets.
There we go. You can see this permanent magnet is suspended underneath this electromagnet. Whenever the permanent magnet moves slightly imperceptibly closer, this little sensor on the bottom here detects that, sends a message down to these electronics, and tells the electromagnet to become a little bit weaker. It turns down the current. And that allows the ball to fall away a little bit. And as it falls away, the sensor detects that again and increases the strength of the electromagnet and pulls the ball back towards it. So one complication of this system is that your feedback system always needs to be working, and it needs to be working very fast. You can see this ball is spinning and wobbling a tiny bit, and that's fine for a little demonstration like this, but if you've got a train travelling at hundreds of kilometres an hour along the track, you're going to need a very, very sensitive and accurate feedback system.
The Shanghai Maglev takes this simple concept to a whole new level. There are 128 sensors in every section of the Maglev vehicle. They feed back the distance between magnets and guideway thousands of times a second, allowing powerful computers to adjust the electromagnet's current constantly and with microscopic accuracy.
This is the guideway, and the train floats 1 centimeter from the guideway. Now that is incredible precision. Now there's a computer system that makes sure that all of the time the train floats at 1 centimeter from the guideway.
The advanced computer system also regulates the running of the whole service, meaning each journey time is predictable to the second.
Now this is the ambition of the Maglev. With computer systems, they've been able to achieve an extremely precise service.
It's taken decades of planning, design and testing to create the world's only commercially operating high-speed maglev. A unique concept that throws away the rulebook for traditional train travel and makes high-speed journeys possible in engineless vehicles.
A system like the Maglev points to the future of transport in our world. Incredible things to be achieved. This shows us that we can get people moving from A to B in short periods of time, which is great.
By drawing on the innovations of the past, adapting, improving them, and making breakthroughs of their own, the designers and engineers of the Maglev have realized the dream of a superfast train that flies without wings, and succeeded in making the impossible possible.
It's kind of unbelievable that there's a train that goes over 400 kilometers an hour. It is a vision of the future, and it's here right now.